Bismillahirrahmanirrahim. Today, inshallah, I wanted to talk to you about the perpendicular bisector theorem converse. Previously, we talked about the perpendicular bisector theorem itself, and we had suggested that the theorem is more about the points that are on the perpendicular bisector than about the perpendicular bisector itself. So the theorem had stated that if a point, such as point C over here, is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. Okay, so we had a perpendicular bisector like this that was given to us, and we had suggested that if a point is on the perpendicular bisector, then it is equidistant from the endpoints of the segment. Now, the converse of the perpendicular bisector theorem is like this. It states that if a point is equidistant, so we start from the equidistant part of it, if a point is equidistant from the endpoints of a segment, then the theorem states then that point is on the perpendicular bisector like this. Okay, so it's like the question is, does it go through over here like that? Okay, so that's the thing. So the theorem states specifically the converse of the theorem. So it states if a point is equidistant, so what's given to us is that, for example, point D here is equidistant from, of course, the endpoints, from the endpoints of a segment. So what's given is that this point is equidistant and from the endpoints of a segment. So if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So the theorem said if a point is equidistant, then you can kind of like imagine like the arrow that's like shooting straight down over here, and then go like that through point D. That's what the theorem says, like that. Okay, so that's what we're that's what the theorem states. Now I typed out over here for you the theorem itself and the converse I've written here. So the theorem says if a point is on the perpendicular bisector of a segment, it is equidistant from the endpoints of a segment. The converse starts with the equidistant part, and then it says it's on the perpendicular bisector. Now, how do we go about proving this? Okay, so now look, to this theorem, if we were to prove this, we would be given, okay, so we would be given that D is equidistant. Right, that would be given. D is equidistant from AB, okay? From A, B, okay? Points A and B. And then we would be asked to prove, okay? Then we would be asked to prove that D lies on the perpendicular bisector, okay? Now, how would we go about doing this, okay? Now, I've written out here for you a little bit more neatly. So now, how are we going to go about proving that D lies on the perpendicular bisector? Okay, well, what if we did this? Okay, what if we proved that this right here, this segment right here, what if we proved right there? Okay, that and let's call this point M over here, the midpoint. What if we proved this point MD right here, this segment MD, is the perpendicular bisector? If we prove this MD right here, this segment right here, is the perpendicular bisector, then of course D would have to be on the perpendicular bisector, right? So if we can prove that D contributes to the making of the perpendicular bisector, so to speak, then we have proven that D is on the perpendicular bisector. And how else can it be not be, right? If it makes the perpendicular bisector, it has to be on the perpendicular bisector. So that is our modus operandum. That is kind of a thought process over here. Now, that's what we're going to try to do. We're going to prove here that DM, the midpoint M, and D actually is the perpendicular bisector. Okay, so now here's the thought process. First of all, we're going to say M is the midpoint, right? Okay, and then we're going to construct this line over here, this segment over here, MD. Okay, then we're going to prove that these two triangles are going to be congruent. Okay, we're going to prove this triangle congruent. Now, in this proof, we can't assume that this is a right angle, okay? Okay, we can't assume that these are right angles, okay? But the reason for that is because that's starting off that that's a perpendicular bisector. So in this, we cannot assume that these are right angles, okay? Now, so what we do say, okay, we find the midpoint, okay? And then we construct this segment MD, okay? And we prove the triangle is congruent. Watch. So this is how we start. All we know is that D is equidistant from AB. So I'm going to write the thought process here, okay? Then we say M, okay? So we say let M be the midpoint, okay? Right, so M is the midpoint. And then you make MD, you make the segment MD. You construct that segment MD, okay? Then we prove that these two triangles are congruent, okay? Then we say triangle A, MD, and triangle BMD. AMD is congruent to triangle BMD. Now, how is that, you say? Well, I have side, side, and voila, I have a side. So side, 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 correct? So these are congruent because of side, 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 okay? Then what you say? Well, after you've proven that that they're congruent, okay, then we say these two angles are congruent, right? Then we say angle AMD is congruent to angle BMD, okay? That's because of CPCTC, okay? Corresponding parts of congruent triangles are congruent, okay? From there, then we say, watch, this is really cool, I think. So from here, we say that angle AMD and angle BMD are what? Are right angles, okay? Why? Then because they're congruent, then we can show that these are right angles. Why are they right angles? Because they are linear pair. This is the linear pair theorem. That is, okay, if two lines intersect to form a pair of congruent linear pair, if two lines intersect to form a congruent linear pair, then they are perpendicular. Okay, then those are right angles. Okay, now look. Okay, then we say MD is the perpendicular bisector of AB, okay, because it's perpendicular and it bisects it. Ta-da! And since MD is the perpendicular bisector, D is on line MD. D lies on the perpendicular bisector. So how beautiful is that? Okay, so let's try to do this again, okay? So we are given that D is equidistant from AB, and we are to prove that it lies on the perpendicular bisector. Well, we're going to do one step better than that. We're going to prove that DM makes the perpendicular bisector. It is on the perpendicular axis because it makes the perpendicular bisector, right? If you could do that, that would be great, right? So that's our thought process. So first thing we do is we construct a segment MD over here, okay? And that's from the midpoint. So M is the midpoint, and we construct this segment here, okay? And once we do that, okay, let M be the midpoint, okay? Then we say MD, okay? We construct the MD. Then we try to prove those two triangles congruent, and that's because of side, side, side. The reflexive property of gives MD. Okay, once we do side, 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 then we say those two angles are congruent, the green ones, AMD and BMD, because of CPCTC. And once we have done that, we say those two angles are perpendicular, those two angles are right angles because of linear pair congruence theorem, okay? So when two lines intersect to form a pair of congruent linear pairs, then the lines are perpendicular. Now we've shown that MD is perpendicular and it bisects AB, therefore MD is the perpendicular bisector, and since we've proven it's the perpendicular bisector, darn it, D has to be on the perpendicular bisector. So hence this is the this is called a paragraph proof. Like this, you can construct a 2-column proof from this, a more formal 2-column proof, which I would like you to do, inshallah, and then you'll appreciate it. So this is the very important perpendicular bisector theorem, and this is the very important perpendicular bisector converse. Okay, perpendicular bisector theorem converse. Please appreciate this, and we shall do some beautiful example questions with these next time. Until then, as-salatu wa-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.